Okay. Today we're going to start shifting gears a little bit into the kind of second part of the class. We're going to do an introduction to vector calculus today, and then we're going to go back a little bit to the least squares type of material that we started with at the very beginning of the class, the first lecture. And then we're going to move into specifically convex optimization. So far we've been doing optimization. A lot of the problems we've considered have been convex, but we've been not using convexity-based techniques to do optimization problems, right? We've been doing linear algebraic techniques to show optimality of solutions. And we're going to now move into the part of the class where we're going to start using the properties of convexity, define what convexity is, convex sets, convex functions, so on and so forth. And a core part of that, development and part of developing those tools is built on ideas around vector calculus. So today's class is kind of setting us up for being able to build out the tools of convexity that we are going to be using in the second half of the class. So we're going to define today basically what gradients, Hessians are, and then we're going to come to what is called the main theorem. And I'm calling it the main theorem after notes by Professor Praveen Waraya. So I recommend looking these up. If you just Google, we'll add them to the course website as well. There's a freely available PDF that has this information. You'll see what the main theorem is. It's basically about how to find optima for general functions with open sets, connecting them to derivatives. You've probably all heard this theorem before. Professor Waraya calls this the main theorem, and he's, one of the greats of the field. He was a professor at Berkeley. He actually very tragically passed away this past summer, which was, just really, really terrible. He was on my thesis committee. I admired him tremendously. And so he calls this theorem the main theorem. And so I'm going to call it the main theorem, and we'll come to talking about it. But definitely look up his notes. He has a set of incredibly elegant lecture notes on convex optimization that, they're very nice. They're written in a slightly different style than the way we're teaching this class now. But of course, all of the material is there, and we'll be drawing on it possibly a little bit later, again, when we get to linear programs. Okay, so with that, let's come to the content for today. So all of you have taken a calculus class before, and so all of you know what a derivative is, right? If I have some function f of x, let's say it's going from r to r, what is a derivative? A derivative says, how does f, for example, change with respect to changes in x, right? So if I consider df by dx, it's talking about changes to the function as the variable x itself changes, right? And in this context, you've probably all seen Taylor's theorem. Right? What does Taylor's theorem say? It says that, for example, let x naught be some fixed point. And if x naught is some fixed point, then it says that if I consider, let's say, f of x plus delta x, well, delta x is now some variation on x. It says I can write this function value, right? I can write the function evaluated at some point close to x in a local neighborhood in terms of the function at x naught itself. And I'm going to write this, so I'm going to write it as x naught, f of x naught plus a correction term. And the nice thing is that this correction term is a polynomial term. right? So we're going to write it as df by dx at x is equal to x naught times delta x plus 1 over 2 factorial d2f by dx squared delta x squared plus, the same, like then you get the third derivative, 1 over 3 factorial delta x cubed. We're going to call these higher order terms. Okay? So what this is a way of approximating f of x as a polynomial, right? Remember, why is this a polynomial? So here, on this right-hand side, what are the variables? Right? Delta x and delta x squared are now the variables. X naught is known and fixed, right? So this is a constant. This is a real number. This term is also a real number, right? This is the derivative evaluated at a specific point, x equal to x naught. This is the second derivative evaluated at a specific point, x equal to x naught. So what the variables are, or delta x squared, so on and so forth, right? This is the deviation from the fixed point that we're considering. People get confused a lot about this, so make sure you know what the variable here is and what is a real number. And this basically gives me an approximation to what the original function is. Now, if I told you nothing about the function, and I told you f of x naught is 2. What is f of x naught plus 0.00001? And you had no information about f. If you had to make a guess, what would you guess? You might guess that it's exactly equal to the value that I just told you, right? That, probably it's not changing that fast. Of course, functions can change very fast. But this is one way of saying, it might be a reasonable guess given no other information. If you had a little bit more information, maybe you knew something about the first derivative. The first derivative tells you something about how that function is changing locally. You could use the first order approximation. If you knew something a little bit more, you could use the second order approximation, so on and so forth, right? And as you increase the degree of your approximating polynomial, you can catch more and more aspects of the function that you're trying to approximate. So the larger the degree that you allow, the less your error is going to be in terms of approximating the polynomial. Of course, this is an infinite sum, right? So to have 0 error, you really have to sum to infinity. This is a limiting statement, okay? But in engineering, we often use Taylor's theorem as a approximation tool as opposed to an equality. This is where it comes in very handy. So just as an example, let's say we take f of x is equal to x cubed, right? So let me draw it. One thing that is very useful in this class and in life in general when dealing with mathematical things, draw pictures, make plots. I learned this from a math teacher when I was in high school, and he would make us draw pictures all the time, and it is a lifelong skill that serves me till today. So if you don't already have this habit, I highly recommend picking it up. So if I have now this x cubed, it looks something like this, right? F of x equal to x cubed. This is my 0. And let's say I want to approximate this function at some point here, x naught, okay? So the first order, or the linear approximation of the function at this point, what is that? What is the linear approximation to this function at this point? Someone else. Maybe make hand motions. Yeah, someone who hasn't participated. Good, yeah. Yeah, a line, right? This is a tangent line here. It is going to be the approximation. Now, what do you notice about this approximating line that I'm drawing? If I try to use this approximating line out here, is this a good approximation? Not really, right? Here it's even worse. But it's pretty good in this small neighborhood, right? So basically, what you want to remember always is that you're looking at these delta x's that are small. The closer you are, the better the approximation, okay? If I wanted to instead take a quadratic approximation, what would I get? I would get a parabola, right? I would get something like this. That would approximate pretty well in some neighborhood around here. But as you then diverge, it would become worse and worse, right? For example, it would have a pretty terrible approximation for negative values because this quadratic will necessarily tell you something positive when in fact your function is negative, right? So as you diverge and you go far away, this is going to be pretty bad. But in these local neighborhoods, it's reasonable. Okay, so this is all a review. All of you have seen Taylor's theorem before. What we want to now talk about is Taylor's theorem. Is this marker visible? At the back? Okay? So here I want to think about this now in the context of functions of vectors. And this is going to bring us to the definition of a gradient. What a derivative tells us is how does a scalar function of a scalar change, right? What we want to now think about is we want to think about functions that are functions from a vector space into the real numbers. So I have a function of a vector that's a scalar. What's an example that we've dealt with a lot that's a function of a vector but returns a scalar? The norm, right? Dot product and norm. So for example, f of x equal to norm x. True norm, but we can be really any norm, right? So turns out we can write a similar expression, and we can write f of x naught plus delta x. So here now delta x is a vector, is equal to f of x naught plus, now I want to write something here that will multiply delta x, right? What do I want to write here? What kind of thing do I want to write? I want to approximate f of x naught plus delta x. What kind of function this is? The scalar valued function, right? The codomain is scalars, all real numbers. This is a vector. So what kind of thing do we need to have here for this thing to be a scalar, right? Because this has to be a scalar valued thing. What do we need to have? A row vector, right? If I put a column vector here, does this you can't even make it work, right? You can't multiply two column vectors. So necessarily, by structure, we know we have to have a row vector here. Keep this in mind because students always get confused about dimensions of gradients. This is one great way to remember whether the gradient is a row vector or a column vector and whether the derivative is a row vector or a column vector, okay? Know that if you're multiplying delta x, you had better be something that is a row vector. So what we're going to write here, we're going to represent it, we're going to call it this notation, gradient of f at x equal to x naught transpose, okay? So this is the gradient. We haven't defined it yet, but this is what we're going to write notation-wise. And now we want to also add a quadratic term, okay? So what is the parallel to x squared? Like when I think of a quadratic in a polynomial, I think of something like this polynomial, for example, is something of the form ax squared plus bx plus c, right? Can I write x squared for a vector? No. What is the parallel to a quadratic term? x transpose ax, right? So I want to have something here that is of the form delta x transpose times something times delta x. A quadratic, the generic quadratic term when you're talking about vectors is of the form x transpose ax. Okay? And so now what is going to be in the middle? What is the second derivative equivalent in the vector context going to be? What is the shape of it going to be? Can I put a vector here? No. What does it have to be structurally? Has to be a matrix, right? So this guy, I'm going to call the Hessian. Okay? This thing called the Hessian. And of course, I could write higher order terms, but we're not going to really go into that at all. Okay, yes, question?
Wait, so I'm just curious, in practice, like, you could do like third order, fourth order?
In practice, the question is, what about higher order terms? Could you do third order or fourth order? In practice, you would almost never do third order or fourth order, just because you're going to get tensors there.
Yeah.
And it's very hard to compute with. There are some, there's research being done on how to use tensors for machine learning. It might be in practice in some places. I don't know. But it's very, very uncommon. One of the nice things, or one of the most common things that people love doing is taking nonlinear systems and approximating them using a strategy like Taylor's theorem. For those of you who've taken 16b have already seen this, and making linearized systems out of nonlinear systems. So the most common terms that are used are just this term, and you can get a lot out of that. On some occasions, you will use the quadratic term, but almost never will you actually use the higher order terms for regular applications. Research applications, it might be used. Yes, question?
What really is like the difference between like a Jacobian and like a Hessian?
What is the difference between a Jacobian and a Hessian? We'll get to that. Jacobians are, you're thinking not of a scalar valued function. Now you have vector valued functions. So it's going to be more complicated. We'll talk about it maybe next class, or talk to me in office hours. Yes? Do I need a 1/2? Yes, I do need a 1/2 here. Thank you. 1/2 factorial. Thank you very much. Okay. So here, what I want to also highlight is that if I look now just at this first order approximation, this red box is my first order approximation. Excuse me. And here, what we are going to have is, what kind of thing is this now? What kind of equation is this? This equation is of the form, I have some, if I call this some vector p, the gradient, let's say some vector p, I have p transpose times some variable x equal to some constant, right? Do you see this? Delta x is my variable. I'm replacing it by just an x over there. And if I just take this, then this minus this is some constant, right? So do you see that this is of some form like this? What is this in general the equation of? What kind of geometric object is this? It's a hyperplane, right? This kind of equation defines a hyperplane where p is your normal vector. Okay? So this, just like in the scalar case, the first order approximation is a line. Here you have a tangent hyperplane. Yes, question? Oh, sorry, b should be a constant, yeah. I apologize. Yes? Okay, how is this equivalent to this? So I'm going to call this thing is P transpose. Okay? This is delta x. So delta x is basically, let's say x naught. Or if I call x naught plus delta x equal to some vector a, then delta x is equal to a minus x naught, for example. However you want to think of this. All I want to say is that this is a generic set of vectors. And if I want P transpose times some set of vectors, right, what are all of the delta x vectors that are permitted to satisfy this? Right? It's going to be everything such that P transpose x is equal to this particular b. So basically, if I was to consider b is equal to 0, right, if I have a normal vector here, what is the set of all vectors such that the dot product with this vector gives me a 0? Right? That is this plane, right? For example, if this table, like this is my normal vector, then it's the hyperplane of this table, right? Everyone see that? So now, if I change the values of this, if I change the b, that's like changing where the plane is in your space, right? So this is why this is the generic equation for a hyperplane, is P transpose x is some constant, right? So now I have, this is a fixed vector. This gives me a real number. This is my variable. So what this defines is a hyperplane. It's a set of vectors given by this hyperplane. Everyone, I think a lot of people appreciated that question. Good. Everyone with me on why this is a hyperplane? Okay. So similarly, if you were to look at this, right, if you were looking at this quadratic, you would be defining basically a generalization of a parabola, which I don't actually know the name for. I don't know what it's not a hyperbola, but I actually don't know what it's called. Maybe someone else does. But you're thinking now of the generalization of a quadratic, right? But the easy thing is the generalization of a line, which is going to be this hyperplane. Okay. So now, let's actually define this gradient a little bit more. Oh, not red, right? Sorry. So I want to now describe how a function changes with respect to a vector. If my vector has n components, there are basically n different things that can affect how my function changes, right? So this notion of this gradient has to capture, change according to all components of x. And so I define my gradient of f of x as I take the partial derivative of f with respect to the first component of x1, partial derivative of f with respect to the second component, all the way up to xn, transpose. So this gradient I'm writing as the transpose of a row vector, okay? So the gradient is always a column vector. The gradient is always the same dimension as x. The transpose of the gradient is often called the derivative, and that is always a row vector, okay? So that's another way to keep this straight. This gives my definition of a gradient, because I'm trying to capture, well, how does the function change with respect to the first component, the second component, all the way up to the nth component. And so it makes sense, basically, that you have an n-dimensional vector capturing this notion of a gradient, right? Because you have n changes to account for. That's why you have n numbers that you're keeping track of. Now, when you want to think about the Hessian, I want to now think of how f changes, not just with respect to every element of x, but with respect to every pair of elements of x, right? So that's why you're going to get a matrix, because now you have to keep track of changes with respect to component xi as well as component xj. Another way to think about it is second derivative is a derivative of the derivative, right? So now you want to see how does the gradient change with respect to x. But the gradient now has n numbers in it. So now you want to see how does this change with respect to x1, x2, x3, x4, xn. How does this change with respect to x1, x2, x3, x4, xn, right? So that's why you get this matrix. So the Hessian I'm going to define ij is basically the ijth component of this matrix is going to be del f divided by del xi del xj. Okay? Now, in general, when you have nice, smooth functions, which is most of the functions that we're going to be considering in this class, the order of derivatives doesn't matter. Orders can be interchanged. This is not generally true, but for smooth, nice, continuous functions, this can be done. And so often, you will end up with Hessians that are symmetric matrices. So one other reason to think about symmetric matrices is that more often than not, Hessians are symmetric. Okay? So this gives us the definition of a Hessian, often symmetric. Okay? Great. Now let's do an example that will help clarify a bunch of this, hopefully. So let's consider f of x is equal to norm squared of x. And let's consider this as just a function from R2 into R. So just a two-dimensional setup, okay? So let's start out by first drawing this function. So what does this function actually look like? So if I consider now the x1 plane, x2 plane, and this is now my f of x, what is the shape of this function? Someone? Some hand gestures? It's a bowl, right? So we have, it's kind of like this. It's going to be like a bowl-like thing. And if we draw the level sets of this, what are the level sets of this function? What is a level set? How many people have seen level sets before? Okay, everyone knows what a level set is. Okay, so why don't you draw the level sets? How many people are done? People done? No? Yes? No one's? Yes or no? Are you done? Yes? Okay. So if you have an x1 and an x2, what are the level sets of this, right? Level sets are basically if f of x is equal to a constant, what are the different values that are taken, right? So now this basically is a way of kind of drawing a two-dimensional picture of a three-dimensional object. So the level sets look something like this, right? Along these curves, the function is constant. Right? They're circles of whatever radius, right? So if I draw a circle of radius 4, then that's the level set corresponding to that particular radius. Okay. So for this function now, what is the gradient and the Hessian? Why don't you compute that? And then we can work it out together. While I erase this board, why don't you compute what the gradient and the Hessian are? So what is the gradient of f of x? Two x1, 2x2, otherwise written as just 2x, right? Why? Because basically you take the derivative with respect to the first component, derivative with respect to the second component. You can write this easily. What about the Hessian? What do you get out? I want to take derivative of this with respect to x1. What do I get? 0? No. 2. Derivative of this with respect to x2? 0. Derivative of this with respect to x1? This with respect to x2? Right? Great. So how does Taylor's theorem work out here? So what is f of x plus delta x, x naught plus delta x? So let's say I choose some x naught, let's say some, or let's just say x, I just expand around some specific x equal to x1, x2, and I want to understand x plus delta x, so that is x1 plus delta x1, comma x2 plus delta x2. Okay? You have this. What are you going to write out? You're going to write out, basically first I'm going to write out the function value at x. So I get x1 squared plus x2 squared. Then what do I have? What's the second term? I'm going to write the gradient, transpose. So I'm going to have 2x1, 2x2 times delta x1, delta x2 is my second term, right? Plus 1/2 delta x1, let me write this on this side a little bit, delta x1, delta x2 times my Hessian times delta x1, delta x2. So let's see how well do we do with this approximation. What does this come out to be when you simplify this? This is equal to x1 squared plus x2 squared plus 2x1 delta x1 plus 2x2 delta x2 plus, this just gives me delta x1 squared plus delta x2 squared, right? And doing some rearranging, this is equal to x1 plus delta x1 whole squared plus x2 plus delta x2 whole squared. So in this case, what is the error in your approximation? 0. Could you have said this? Could you have guessed the error in your approximation without doing this calculation? Yes. Why? It's a quadratic, right? So there's nothing much to be, like, of course, what is the best quadratic approximation to a quadratic function? It's quadratic, right? So, good. Basically, everything works. Don't forget the half, right? If I'd forgotten the half, this wouldn't have worked. So make sure you remember all of these constants. Okay, good. Next example. F of x, consider, equal to x transpose A. What is the gradient of f? Question?
Yeah. Could you repeat the assumptions for symmetric hashing? What are the assumptions?
Basically, smoothness of your function. Continuity and smoothness. You want to have the derivative be interchangeable. Oh, right. One thing I wanted to point out, I totally forgot. But coming back to this example for a minute, sorry, I forgot about this. What does this tangent hyperplane look like in this case? What would it look like, for example, over here? What would be an approximation to these? If I were to draw this in the level set sense, I would want to have basically these kind of lines, right? So here, any approximation, remember, is going to be like a tangent hyperplane to this surface now. Right? And your gradient is going to be the normal direction to that hyperplane, to the tangent hyperplane. Okay? Something to keep in mind, because we'll be using gradients a lot when we get to gradient descent type of algorithms. So, something to keep in mind. Okay, coming back to this. So here, now we can write this as basically, if I have entries of this quantity is equal to sigma xi ai. And so what is the derivative of this when I take it first? The first entry of this is going to be when I differentiate it with respect to x1, I get a1, a2, all the way up to an, right? Is equal to just the vector A. So I want you to know how to do these calculations. I see a lot of students basically, when you start using vector calculus in your machine learning classes or any other classes, people just look up the matrix cookbook. For those of you who haven't seen this, it's like basically a set of 20 pages or 30 pages of formulas on derivatives of matrices and vectors, right? It's very useful, but most people who use the matrix cookbook have no idea where those formulas actually come from and why they're correct. This is the math behind why these formulas actually work. One of the things that you should know is that there's in this cookbook, sometimes there's subtle errors on transposes and things like that. So if you're using the cookbook, something goes wrong, it might be that you're using a wrong formula. So always make sure that you can go back and verify. Okay, so it's important to know what's going on underneath the hood. But this is the most basic example. Everyone good with this? Okay. Let's go to now a second, slightly more complex example. F of x. What's the next most interesting function that's scalar valued? X transpose AX. So I'm not going to do this one out right away. Take a minute, try to do it out, work it out yourself, see where you get stuck or where it's easy. Oh, okay, let's do it out together. Okay, so to find the gradient, what do we want to do? We want to basically find entry-wise what is the derivative of this with respect to all of the entries of x, right? X has components x1, x2 up to xn. So in this is a scalar, right? Let's write this out. So this is equal to x1 all the way up to xn times this matrix a11, a12, all the way up to a1n, ann, x1, x2, xn. So can you write this out in terms of the terms one by one? What's going to happen when you do this multiplication? Right, you're going to have this row times this column, this row times this column, so on and so forth. So what are the entries of A that are going to multiply x1? Right? Everyone here is going to multiply this x1. So what are the terms? Sorry, the first column is going to multiply x1. Right? The first row times this, second row times this. So x1 gets hit by everything here. What are the things that are going to hit this x1? It's going to be everything along this row, right? So can you write out what are the entries? What are the terms that say have x1 in them? If this is complicated, okay, everyone, what do you do when you have a big problem that is like, I don't know what to do? Do a small one. Everyone write out the 2 by 2 and do it now. Okay, so coming back, right? So I know basically that everything that is going to hit entry x1 is either in the first row or the first column. You should have seen this in your 2 by 2 example, right? Does x1 ever get hit by A45? It does not, right? So I can write this as a summation. So what if I have xi? Every term is going to have something from this row vector, some term from here, and some term from here, right? So xi can be hit by basically aij times xj, right? I take this, take the row element, and then I take the corresponding. Every term can be written exactly like this. And I write this as a summation over I and a summation over j. Okay? This is not hard, right? But it's important to remember, like if it seems kind of daunting, just break it up into simple pieces. Do the basic step. Do the 2 by 2 case out. You'll see that this follows immediately, right? You'll be able to generalize. Okay? So now, what is the derivative of, so now basically, what are the terms? I can basically isolate what the terms are, right? So what are the terms that have xi in them? What are the terms that have an xi? It's going to be xi, aij, xj, plus xj, aji, xi, plus right? Plus 2 times x I a I. Right? No. What do you mean get it 2 times? Will I get it 2 times? I get an xi square, sorry. Not a 2 times. A little aii. So now when I take a derivative of this, when I take df, or partial, sorry, not even the derivative, the partial of f, with respect to xi, what am I going to get? This gives me aij xj plus xj aji plus 2xi aii. Right? Yes? What are the terms that have xi? Okay. So let's look at this summation, x over xi and xj, right? So let's just say, what are the terms that have x1? Okay? What has x1? So x1 can either come from this side, or it can come from that side. Okay? So I could have x1 times a1j, and then I'd pick up an xj from this guy. Or I could have something else come here. I could have I could start with an xj, then I'd pick up the jth row, but then I'd pick up the x1 over here. So I would have an xj aj1 x1, or indices might be the other way around, but you get the point. Or I could have basically x1 a11 x1, right? That's why these are the three terms that you would get. So I get this expression, right? So now can you write out the gradient? So how can I write this? Is there a nice, concise way to write this in a summation format? So I can write del f by del xi. Oh, wait. Did I make a mistake? Yeah, there's a mistake here. What's the mistake? What are all the terms that have xi? There's a mistake here. Am I double counting? I'm like under counting by a lot, right? Basically, I'm going to get x1 with x1, x1 with x2, x1 with all the way up to xn. So I totally messed up here. I should have read from my notes, but I just tried to do it on the fly. So what should this be? I should have a summation here, right? I should have a summation over j, and I should have a summation over j here, right? And this is j not equal to I. Sorry about that. Okay, that's why everyone was confused and quiet. Okay, good. Sorry. Ask a question. Sorry, I just made a typo. I'm totally sorry. Everyone with me now? Okay. See, this is why you shouldn't copy out the matrix cookbook. Maybe they forgot a summation. So now this gradient, this is totally wrong. What should this be? What should I have here? I should have a summation here, and I should have a summation here, right? So I can write this now as a summation jointly over aij plus aji times xi over all j. And I'm basically pulling this into this and allowing j to be equal to I. Right here I had j not equal to I. So I can write it in this concise format. Okay? Yeah? Is it xj? Yes, it should be xj. Ah, thank you. So now what's a nice way of writing this out? Turns out I can write this concisely. So I basically want to add everything to its reflection across the diagonal, right? What are things that connect reflections across the diagonal? What's a matrix that does this nicely? A and A transpose, right? So if I considered A plus A transpose, what would the entries of this matrix be? Would this be a symmetric matrix? Would it? I think it would. What would be the ijth entry of this matrix? Aij plus Aji, right? So I can write this. This is basically, now this is a, can I write this as a matrix vector product? What's the vector I want to multiply this about if I want to have these pop out? I can write this as basically just x1, x2, all the way up to xn. And so basically, this gives me this gradient that I want to write as of f of x equal to this. This is for every entry, so I can generalize it for now the entire thing. I'm stacking them all into a vector. And now from this, what's the Hessian? I just want to take the gradient of this again with respect to now this vector x, right? This is now, I've already done something like this. I haven't actually done basically A times x, but this will turn out to be A plus A transpose. Okay? Yes?
What happened to the
xi squared aii term got pulled into here because this became a 2xi aii. So aii plus aii gives you 2xi aii, and I remove that. Okay? So verify this. If this is not fully there yet, verify this after class. I want to use the last 15 minutes of class to go over this other theorem. So this is a index accounting calculation, okay? Any last questions about this? Yes? Oh, we're assuming that A is a square matrix because otherwise this matrix product wouldn't make any sense, right? Because we have n-dimensional vectors on both sides. So A is square. We're just assuming that this quadratic form only makes sense when A is square. Because x and x transpose are both are n-dimensional, right? Okay. So why are we going to do all of these calculations about gradients and Hessians and derivatives, right? What is the point of all of this? And the point of all of this is because we want to be able to use what I'm going to call this the main theorem when we're doing optimization. And you've all probably seen this, right? If you have a general function, if I have some general function f, and let's say it's some function from Rn to R, and let's say it's differentiable everywhere. Then I want to consider the optimization problem. subject to x belongs to, let's say, some omega, where omega is an open set or open subset of Rn. Okay? So what do I mean by open subset? I mean that it has no boundaries. A set that does not include its boundary is an open subset. Okay? So for example, on the real line, the open interval between, let's say, -1 and 1, so basically all points that are infinitesimally close to 1 are included in the set, but 1 is not included in the set. This is an open subset. Whereas if I was to consider the closed subset, -1 to 1, so I include all the points before 1 and 1, that is a closed subset. A set that includes its boundary is called closed. If it does not include its boundary, it is called open. Okay? So omega is an open subset. Then, if x star is an optimal solution of this optimization problem, what should I call this? Of this optimization problem in the red box, then df by dx x star is equal to 0. So what this is saying is that the optimum value is attained at a point where the derivative is 0. Okay? So probably people have done things like this already, optimizing functions in a calculus class, maybe by taking the derivative, setting it to 0, and then finding the optimum, right? You may or may not have actually proved this theorem. It's actually unlikely, unless you've taken a real analysis class, you probably never proved that this is actually true. We're going to be doing this basically for the rest of the semester. So today what we're going to do is we're going to prove that this is true. And this is what it's called. This is why it's called the main theorem, right? Because fundamentally, a tremendous amount of optimization is built off of this idea, is that whenever you're at an optimum point, you're not changing very much, or your derivative is very close to 0. And intuitively, this kind of makes sense, right? Think about a parabola, for example. You're not changing very fast at that, when you have some big bowl like this, at that bottom point, you're not changing very fast. Your derivative is basically 0. So if I had some general function, right, if I think about some general function like this, any optimum point, whether it's going to be a max or a min, is going to happen at locations where your derivative is 0. That's what this theorem is saying. Note that this is not saying that every time your derivative is 0, you have an optimum point. It is saying that if you have an optimum point, then your derivative is 0. Okay? We will then go on to talk about convex functions. And convex functions are such functions that they have the property that all local minima are global minima. So basically, you only have one kind of dip in the function like this. And then we will be able to say, well, because it's convex, if I set the derivative to 0, I'll be able to find the optimum point. Yes, question?
Is the reason we don't consider endpoints because we're on an open set?
So the question is, why don't we consider endpoints? So that's a very good question. So let me answer that. So the basic idea, and we will talk about boundary points and things like this once we get to LPs in the class. But let's just consider the function x squared, right? F of x equal to x squared. X squared, we know the minimum point, just intuitively, is at x equal to 0, right? But now, let's say I asked you to minimize this on the set, instead of all over Rn, between 1 to 5. Minimize f of x between f of x equal to x equal to 1 and x equal to 5. What is the minimum value of this function now? It's at 1, right? Is the derivative 0 at 1? It's clearly not. So this is happening because of the fact that you're interacting with a boundary. And so what you will see, and this is, for example, one of the things that comes up in LPs, for those of you who've taken 170, you've seen this already, which is that optima are attained at boundaries or at places where your derivative is 0. So when you're looking for places to find an optimum point, you're going to search over boundaries and not. So here we're considering an open set so that we don't run into situations like this. In this case, on this open set 1 to 5, there is no point where the derivative is 0. Do you see that? So here, you know, you're like, this is not going to show up. And again, this is important. What this is saying is that if x star is optimal and it's an open set, then you can guarantee that the derivative is 0. So here's a counterexample of a non-open set where you have an optimal point where the derivative is not 0. Does that answer the question? Good question. Yes?
As an extension of that question, just to clarify, you mentioned that if it's an open set, then this function is not minimizable. Basically, is that what you were saying? Or,
Oh, no, if it's open set, the function is totally minimizable. Like, for example, if I just considered all of Rn. So if this was an open set here, you would the minimum would not be attained. In this case, you would have what is called an infimum, which is basically, we'll come to it. Don't worry about this just yet. But an infimum is basically a lower bound on all of the values that you can take in this of the function. So it might not be attained. You might not have a value that actually attains it. We will usually end up using minimum and infimum interchangeably in this class because we're not considering these kind of limiting situations. But here you would still say that the minimum is attained, or the infimum is at 1. It's not, the minimum is not attained in the case that this is an open set. But again, the same issue holds in the sense that the derivative is not going to be 0 at that point. Good questions, good questions. Okay, so let's prove this theorem now. I'm going to prove it in the case of just the scalars. So it's just going to be from R going to R. But the proof is exactly identical for any Rn. This just makes the notation slightly easier. What I want to get across is the key concept of the proof, okay? So to prove this, we're going to consider Taylor's theorem. And so let's consider basically the function in the local neighborhood of this point x star. So if I know x star is an optimum point, I'm going to consider f of x star plus delta x. And I can write this as f of x star plus df by dx at x star times delta x plus, I'm going to call this things that are order little o of delta x, right? So this is all quadratic terms and higher. I'm going to call this HOT for higher order terms. Okay? I really only want to care about this first term, linear approximation, okay? So I'm expanding. So I know that basically f of x star is a minimum. So I have this picture here, right? This is my x star. And this is allowing me to understand the behavior of the function in some neighborhood around this space. In fact, it's a linear approximation, so it's kind of some behavior like this, right? I know f of x star is a minimum. This is the minimum. So I can write that basically f of x star had better be less than or equal to f of x star plus delta x, right? This is some other value. This is the smallest value. So I can clearly write this. Okay? Now I'm going to use the fact that I have an open set. So let's say this is my omega, right? This is some omega, or in this case, since I'm considering a real line, I could only consider a real line, but in the interest of generalization, I know that basically I can approach the boundary and be arbitrarily close to a boundary, but I know that I can never be exactly at the boundary, right? That's what the meaning of an open set is. What that means is that let's say x star is somewhere here. It means that I can always find a ball of radius epsilon that is around x and that is also always inside the set. So if I was to think about this in the terms of the reals, let's say this is my open set here. Let's say this is my x star here. I know that I have some epsilon such that in both directions, if I move by epsilon, I'm still always inside the set. Okay? So I can always find some epsilon that is always strictly greater than 0 such that x star minus x is less than epsilon, and x belongs to omega, right? There's a set of points x that are close to x star, less than epsilon away, and that are all in the set. Okay? So now I'm going to choose 0 to be smaller than some delta x to be smaller than epsilon. So I'm going to make sure that my delta x is small enough to make sure that, whenever I'm perturbed by delta x, this guy is always going to remain inside my set, right? I'm going to choose delta x small enough. And then I'm going to use basically this substitution, okay? So I know that this is equality. So let me call this maybe, what should I call this? I should call this 1, and I should call this 2. And substituting 1 into 2, I get that f of x star is less than or equal to f of x star plus df by dx at x star times delta x plus these other higher order terms. Right? Nothing fancy here. These things obviously cancel. So I can write 0 is less than or equal to df by dx times x star times delta x plus my higher order terms. Now I'm going to divide both sides of this by delta x. Delta x is a positive quantity, right? So I can divide both sides by this quantity. Nothing should change, right? What's going to happen when I divide both sides by delta x? I guess I should write over here. divide by delta x, I get 0 is less than or equal to df by dx at x star plus these things that are basically things like delta x whole squared divided by delta x, or some constant times this plus some constant times delta x cubed divided by delta x, and so on and so forth, right? When I divide both sides of that, I get something like this. This delta x here disappears because I've divided it out. Now I'm going to take the limit as delta x tends to 0 of this equation. Is there a delta x in the first term? No. So is this going to move as delta x becomes smaller? No. What's going to happen to all of these terms? They're going to go to 0, right? Because basically this delta x cannot cancel out. There's always going to be a term here that's going to 0. And so the limit of all of these terms is going to go to 0. And so I have established that 0 is less than df by dx at x star. Okay? This clear? So now I don't know, I haven't proven anything yet, right? I've just said that I know that this had always better be greater than or equal to 0. This is the derivative. I want to prove that this is equal to 0, right? I haven't proven that yet. All I've proven is it's always greater than or equal to 0. It can never be strictly negative. But now, what if I did this entire proof? What if I did the exact same calculation with negative delta x? So instead of writing all of this out, I could write this with a minus sign here, right? I could have a minus sign here. Remember, I can move in both directions. And then I would have a minus sign here and a minus sign here. This would have a minus sign here. This would have a minus sign here. Everything would have a minus sign. Minus sign here, minus sign here. Okay? My delta x is still positive. So when now I divide out delta x, what am I going to get? I'm going to get so I have 0 less than or equal to df by dx at x star times minus delta x plus higher order terms. Now again, I'm going to divide by delta x. This time, it gives me that 0 is less than or equal to minus df by dx at x star, right? Do exactly the same thing. Divide by delta x, take the limit. Everything else will disappear except for this term. And so now I have df by dx star, df by dx at x star is greater than or equal to 0, minus df by dx star is also greater than or equal to 0. What is the only value that this derivative can take? 0. Hence, df by dx at x star is equal to 0. Okay? So do you see how we clearly used the fact that we were in an open subset? That mattered, right? In this proof. So now that you have this, we are now kind of at a basis by which we can then start moving into convexity. Not next lecture, but 2 lectures after that, we will start moving towards convexity and understanding more properties of these things. So thanks. See you next class.